We start a new session about thin structures, and I introduce Professor Karam Sab, who will present a joint work actually, entitled A Stress Gradient Model for In-Plane Loaded Multilayered.
Sorry, you are too polite.
No, really?
You have to shout.
Okay. So we start a new session about thin structures, and I'm pleased to introduce Professor Karam Sab, who will present a joint work about the stress gradient theory.
So this talk is dedicated to derive a stress gradient material from a heterogeneous material. So I'm in the same idea to postulate a model and then to find if it is something which is conforming to this model. So I'm not saying that every heterogeneous material should be modeled as a stress gradient material, but I will show you a material which is suitable for this modeling. So we know that strain gradient model can be obtained by upscaling from heterogeneous material. We have seen many presentations dedicated to this issue. We know also that stress gradient materials are different from strain gradient material. Sebastian showed us this yesterday from the consequences on micromechanics. And the question I'm addressing now is, can we derive a stress gradient material by upscaling a heterogeneous material? So the answer is yes. And to show you this, I will consider a multi-layer material which is loaded in in-plane loading. So I will construct a statically compatible stress field in this multi-layer material, and then I will derive from this construction the stress gradient model, and finally I will compare the prediction of this model with finite element computation. So what is the 3D problem I'm interested in? So you can consider a multi-layer material, a plate. So there are many of the main ingredients of my model is that it's a plate. So we have a thickness here which is small with respect to the other dimension. We assume, for convenience, some symmetries on the elasticity. So we assume that C is monoclinic, avoiding coupling between some components. We assume that we have a multi-layer material, so it is heterogeneous, and that the loading is an in-plane loading which is symmetrical and avoiding out-of-plane deformation of the plate. So when you solve this problem from 3D with 3D elasticity, you find out that the out-of-plane component of the displacement and the out-of-plane shear stresses are odd in the thickness, while the other components are even. So by the way, if you take the average value of the out-of-plane component, it's 0 because it's odd. So you are really in-plane loading. So this is a 3D problem, and when you analyze this problem with respect to the small variable, which is the thickness over the size of the plate, you find out by asymptotic analysis that the leading order the strain, the in-plane strain components are this form here, are uniform in the thickness. You find out that the out-of-plane stresses are 0 with respect to this leading order, which means that you have the plane stress assumption, and so you can express your in-plane component, stress component, with respect to the in-plane strain component using the well-known plane stress stiffness, which is obtained from the 3D stiffness via this formula. So when doing this, now we shall take the average of these fields over the thickness, and we introduce the following notation. So this brackets here means that we take the not the average, sorry, it's the sum over the whole thickness. And of course, we introduce normal membranal stress by considering the sum of sigma alpha beta over the average, and we find that this is linearly expressed in terms of the in-plane strain components. And we recover, which is very well known in plate theory, that N is linked to the in-plane deformation here, in-plane strain, via a tensor A obtained from the the plane stress tensor by integrating this plane stress tensor over the thickness. Now we try to express sigma alpha beta, the in-plane stress component, 3D stress component, in terms of the normal stresses, the membranal stresses. So we can express this by using by using this relation here. We can express E in terms of N and plug it here. And so we define what we can call a localization tensor here, which relates the 3D in-plane stresses component to the membranal tensor. And this is explicitly known in terms of this localization tensor is explicitly known once you know the material constituents. And it has the property that if you take the sum of this localization over the thickness, you find identity, which is normal because the sum of sigma alpha beta is n alpha beta. Now, the problem is to find from this sigma alpha beta the out-of-plane shear stresses by using the 3D equilibrium equations. So this is very easy. If you know sigma alpha beta, you can integrate this equation, and you find out that sigma alpha beta will be expressed via a localization stress here, localization of the stress, where you have the gradient of n, which is used here, and here you find the loading, the imposed loading on the plate. So here we introduce the gradient of n, and we have some nice properties for this SP. which is obtained by integrating the above introduced Sn. And here we have this symmetry, which is derived from the fact that n alpha beta is equal to n beta alpha, so p alpha beta gamma is equal to p beta alpha gamma. Now, if you write the boundary condition, the upper and lower upper bound on the upper layer boundary condition, you retrieve the well-known equilibrium equation, where the identity of P is nothing else than the divergence of n, which is very known, and here this vector is a vector of imposed forces of the loading which is imposed. So here I use a decomposition which was already introduced by Sébastien, where I decompose P in terms of a deviatoric part and a symmetric part. And what is said here is that, excuse me, by the spherical part, what is said here is that the spherical part of the gradient of n is known, is imposed by external loads, which is equal to G. Yeah. Okay? So now I have construct a statically compatible stress field. I'm introducing my stress gradient model. So the idea is that you take this stress distribution, you assume that your stress distribution is known as in terms of n and PD, and you know that if you want to have, if you write the 3D equilibrium, you will find that you will find out that n should be that the gradient of n should be equal to this. In fact, it is not exactly we don't recover exactly the fact that the gradient of n is equal to this PD minus these quantities. We find that this is the projection of S with respect to on the set S of this gradient, which must be equal to this. This is due to the fact that you are not sure that Sn is a complete you are not sure that when you write Sn gradient n plus this equal to 0 for all x3, we are not sure that Sn has its kernel is 0. So there is some the kernel of Sn may be not 0, and you have to make the projection over this space S, which is generated by Sn. So this S space has at least dimension 2, and if it has exactly dimension 2, this means that only the spherical part of the gradient of n is completely given by G, and PD is equal to 0. So this will be the case, we'll see it later, when the material is perfectly homogeneous. So once you have written the equilibrium equation, you minimize the complementary energy over the unknown, which are n and PD. And here I made an approximation, because in taking here in the complementary energy, I neglect the contribution of sigma 3,3. But in order to simplify the model, I neglect this contribution. If you wanted to do this, this would introduce the second gradient of n, and I think that it's enough to restrict ourselves to the first gradient. So once you minimize this, after this minimization, you can find the kinematics of the model by a dualization. So the kinematic of the model is as follows. So it's a generalized displacement, U, which is in the space S. And naturally, this generalized displacement can be decomposed into a deviatoric part and a spherical part. And the spherical part is the usual displacement, let's say, U, and the deviatoric part is the additional kinematics introduced by our model. The equilibrium, the weak formulation of the equilibrium equation is as follows. Here we see that it's the diversion of U which is introduced, and this means that this is the dual strain associated to N, and UD is the dual strain associated to PD. Another important feature is that at the boundary we have this integration here, which means that if the plate is completely fixed, restrained at the boundary, this means that the condition is that U dot N is equal to 0 at the boundary. And in the opposite boundary condition, if the plate is free at the boundary, we have to put N equal to 0 at the boundary, which is unusual also. So we recover the generalized strains here. This is the conventional part, and this is the additional part, and this shows you that UD is only the deviatoric part of U. Now, the quantitative equation is obtained by deriving the energy, and we can calculate the relation between E and N, and UD, PD, and some pre-strain which appear naturally, and everything can be computed in terms of the elasticity of the multilayer, and these are the formula here. They are not complicated. Everything can be done in a closed form way. So you have all the ingredients, of your model, and we can also identify with this model the meaning of our kinematics. So our U here is the sum of our in-plan 3D displacement weighted by the localization Sn. So we have a clear meaning of our generalized displacement here, and we can go in the other way. So let us assume that we have a solution of our stress gradient material. Can we reconstruct the 3D problem, the 3D solution? Our proposition is to use from the knowledge of our stress gradient solution, we can compute the stress and the strains, and by integrating the strain, we can recover an estimation of the 3D solution in terms of the stress gradient solution. So this is here I use an integral here in the sense that we ensure that the 3D solution is compatible with the stress gradient solution. Okay, so this is the theory and how we derive it, and we have tried with Arthur excuse me, I have to check that if the plate is homogeneous, we recover a simply plan stress model. And indeed, if you have a homogeneous plate, all these quantities which I have introduced can be computed, and you find that your tensor A is equal to T times C sigma. We have all these quantities which become either zero, either equal to identity up to some 1 over T, and all your introduced variable becomes zero, and everything degenerates on a standard plan stress model. So our model is really linked to heterogeneity of the material, and we wanted to check the prediction of this model on some examples. So we have considered a sandwich plate model made of isotropic materials with high Poisson ratio contrast and identical Young modulus. So we made an experience with uniaxial traction, which means that at the lateral boundary we have imposed a n equal to 0, which is the unusual boundary condition. And we have derived this, derived closed-form solution for the stress gradient model, and we have compared it with full finite element results. So this is the experience here. So we have the structure. Here we have 3 boundary conditions. So the axes are 1 and 3 here. And we plot, we show you the N22, which is the distribution of the normal in this direction. And what is expected here is that if you have a plan stress theory, of course it's uniform. You will have something which is uniform, which is equal everywhere. When you compute this by finite element method, you will see something strange, not strange, but it's not equal here. You will go like this. So this is the finite element method, and this is the result of our computation. You can notice here that in our computation we have imposed that N22 is equal to 0, which means that, and this is very unusual, which means that the stress in this direction is imposed to 0 in our model. And of course, in a standard model, it's not imposed. But what is amazing is that in the real 3D material, it's very close to 0. So how do we explain this? So the explanation is as follows. This, we can see here the stress localization in the direction 2, 2. So normally the average is equal to 1, and you have your constant, your stress here, which is like this in the upper layer, and here in the core of the sandwich. Now in the other direction, in the direction sigma 1, 1. So let me recall you the axis. Sigma 1, 1 is this one. Oh, excuse me. So in this direction. So in this direction, of course, you should have 0. The sum of this must be 0 because you have no in the average, because you have must be equal to 0 here in the average. But we have so different values here with 0 as average, and the idea, and this is sigma 1, 3 obtained by integrating this on the thickness. So if you want to obtain here at this boundary, if you want to obtain sigma 1,1 equal to 0, and you have imposed that sigma 1,1 is obtained by the calculation of n22, so you have to impose that n22 is 0. So this is the explanation of this strange boundary condition that is obtained by our model. So I think that I have presented you the main feature of our model, and I thank you for your attention.
Have you any experience of strain gradient? How does it work in the same problem?
I didn't try it, but I believe that in this case it would be very hard to mimic the boundary condition. I think that our model is very suited to capture layer boundary conditions, boundary layers related to free boundary conditions, while maybe a strain gradient material may be adapted to other kind of boundary conditions.
In the example, the quotient coefficient is very small from the inside. If you have a quotient ratio that, let's say, about 0.1, still the effect is
I think that if the contrast is small,
yeah,
it will you will go toward the homogeneous material, and the effect of stress gradient will go to 0. This is rigorously shown here. If you
no, it's not just for the amplitude of the effect.
These are preliminary results, and we should try to much more laminates and
Usually about the modulus, why did you choose to have the same modulus?
the same modulus. It was
Imagine that more contrasted modulus, you have
yes, we wanted the minimum contrast, and saying that even if Poisson ratio only differs, shall we see this or not? So we wanted to of course, if the contrast in the Young modulus is very high, we expect that we will amplify our effect. But here, even if you have the same Young modulus, you capture the effect of the boundary, the free boundary condition.
We illustrate the fact that it is a frustrated Poisson on the boundary.
So here you have an interesting length which explicitly depends on the ratio of Poisson solutions.
But it's a combination of the ratio between thickness and L here, and the span of the model, and the contrast of the boundary condition. Yes, it's explicit.
I think it's a rational fraction of the Poisson summation.
Okay.
Other questions? So I was told by Navier that this is our last presentation for this morning.